Hello, and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video, we're going to go through basically the last few tests for convergence and divergence. And I usually have a lot of students enjoy this particular section because the tests that we'll deal with, particularly near the end, the last two tests, are a lot of people's favorites because they're very, very quick, they're very clean, and they apply to a lot of concepts that we would have trouble with otherwise. But before we get there, we're first going to address other terms that could have both positive and negative. In the last section, we talked about the alternating series test, where you could have alternating positive and negative. So one's positive, the next is negative, the next positive, the next is negative, and it keeps switching there. But what if it's not that clean? What if it's something like this, where I have color-coded? I have 1 plus 1/4 minus 1/9 plus 1/16 plus 1/25 minus 1/36 plus 1/49 plus etc. etc. So two terms positive, then the third negative, and then two terms positive and third negative. This doesn't necessarily apply directly with the alternating series test because it's not truly alternating. There's two terms that are positive for every one term that's negative. So these are a little bit harder to deal with. There are ways of addressing it, of maybe combining the positive into one and trying to come up with a series that comes up with or generates both the positive and negative version, or maybe come up with a series that comes up with three terms at any given time. That could work as well. However, that's more complicated than necessary. What we're going to address here is basically what we really mean when we say convergence. Up to this point, we've kind of been using convergence rather loosely when we define something as convergence or divergence. However, what we often meant when we were going up to this point was absolute convergence. If we treat something as absolutely convergent, then that means that the absolute version of all the terms converges. Basically, all the positive tests that we've done up to this point, like the integral test, have all been with absolute convergence. The only one that's been a little bit different is the alternating series test, which actually tests the terms that do include the negative versions. The reason we talk about this is because if we could show something is absolutely convergent, or if the absolute value of each of the terms, that series is convergent, then that means the original series is convergent as well. That essentially means that in a complicated series like the one above, with some weird positive amounts of terms and a weird amount of negative terms, we can instead just look at the positive version of everything, and if that converges, then if I just sprinkle in some negatives throughout there, that won't change the convergence. Now, in order to apply that, it's relatively simple. For example, the one that I had above for the 1 plus 1/4 minus 1/9, if I call this my sum of a sub n, then when I look at the absolute value of those terms, what I have is 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25 plus 1/36, all the positive versions of these, etc. And this series I should be able to define. I noticed the denominator just squared numbers. This is actually just the sum of 1 over n squared from 1 to infinity. That's what this absolute value of a sub n is. And this, the sum of 1 over n squared, converges. And we recognize that it converges because it is a p-series by p-series. In this case, because p is equal to 2, which is greater than 1. So we know that it converges. So that means the sum of a sub n, our original series, also converges by what we had above, the absolute convergence test. If the absolute value of the sum of all values converges, then the series will itself converge. Or you can simply say that the sum of a sub n is absolutely convergent. So it converges because its absolute value version does also converge. Now, since we've kind of specified that, we've talked about that up to this point, usually we meant absolute convergence when we actually were talking about convergence. That thus means that there is instances where you have convergence that isn't absolute convergence. Because otherwise, why didn't we just call it absolute convergence? Why is there this specification here? If you don't converge absolutely, then what we have is that you converge conditionally. You converge under some specific terms, but not all the time, not when we take the absolute value of each of the terms. The main example of that is the alternating harmonic series. The harmonic series, as we know, diverges by the p-series test, but the alternating harmonic series, which was the first example in the previous section, converged instead by the alternating series test. So it converged when it was alternating, but not when it's absolute. So we call that conditionally convergent. Another example of that is here, the sum of -1 to the n plus 1 to the 1 over square root of n. Now again, most alternating harmonic series, or alternating series rather, usually have -1 to the n minus 1, but this doesn't really matter. -1 to the n plus 1 is the exact same thing, more or less. It's still alternating, so we can try to talk about what would happen for the alternating version of this, and then also for the absolute. First, the absolute, because if we can show that it's absolutely convergent, then we're done. We don't need to address the alternating version. But if this, or really the whole thing, if this whole thing is a sub n, then the sum of the absolute value of a sub n is the sum of just 1 over root n, which is n to the 1/2. And this diverges by p-series. So that means our sum of a sub n is not absolutely convergent. But if we address the alternating series test, we look at both the limits and if it is increasing or decreasing. Well, the limits of, in this case, b sub n, which is just these two terms, or these pieces here, so the limit of 1 over root n as n approaches infinity is 1 over infinity, which is 0. That's one of the conditions for alternating series. And the second, we just need to show decreasing. And we can do that by 1 over root n plus 1 is less than 1 over root n. The denominator over here is slightly larger all the time, so this is always going to be true. So it converges by alternating series tests. So, overall, that means the sum of a sub n, our original summation, our original series, converges not absolutely, but conditionally. That would be our final answer. It converges conditionally because it converges when it's alternating, so when it's in its form as it is right now, but if we look at the absolute value of that, it actually diverges. It diverges by p-series because 1/2 is less than 1. So that means it only converges conditionally, under the condition that it stays as alternating. From now on, we'll usually address things as absolutely convergent or conditionally convergent. Overall, what this means is that not much needs to change. For example, things like the integral test and geometric series and stuff, those are all using positive terms anyway. So those were already checking absolute values. So those were already checking absolute convergence. What this really just means is that when we're dealing with alternating series or series that include some negative terms, then that is where you're going to need to be careful of either absolute or conditional convergence. But for anything that's just all positive terms anyway, it's just going to show absolute convergence. So that's one note about absolute and conditional convergence, which really kind of ties into the previous section. But our last couple tests, the ratio and root tests, are going to be kind of new, and they're very, very similar, which is why I have them next to each other. Both of these are going to be helpful to try to evaluate either alternating or normal series, which is kind of nice that it has that flexibility. And the way that it evaluates them for both the ratio and root test is by evaluating limits, where the ratio test makes a ratio of successive terms in the series, whereas the root test finds the nth root of the nth term in the series. When we find each of these limits, we find what that limit equals. If that limit is found to be less than 1, then we have that the series is absolutely convergent. And it's also absolutely convergent because, as you see in the definitions here, for how we set up the limits, we take the absolute value anyway. So any of those pesky -1 to the n plus 1s are going to go away. They are going to be irrelevant. If L is greater than equal or greater than 1, then the series is divergent. If L is equal to 1, it is inconclusive. And these three conditions are true for either test. So that's kind of why they go hand in hand. You will typically use the ratio test whenever you see any constant taken to an unknown power of n taken to some constant power, or if you see factorials. Those are usually the three common things to look out for the ratio test. I even have those noted here. N factorial, r to the n, or n to the n, where r is some constant. If you see any of those, the ratio test is a pretty good idea. The root test is a lot less flexible. It's really if you see everything taken to a power of n, that is where the root test is nice, because it tries to eliminate that directly. Now, because the ratio test is good for n factorial, r to the n, and n to the n, it's good to understand the strength of those. Which one of those goes faster than the other for when we are trying to evaluate limits. Generally, for r to the n, n factorial, and n to the n, the inequality follows like this. Any constant to an n power will eventually be less than n factorial, and n factorial will eventually always be less than n to the n. And actually, n factorial will strictly always be less than n to the n. We had this first relation a while ago of r to the n is less than n factorial. That will eventually be true because r to the n is taking one number and multiplying by itself multiple times. So even if r is a number like 100, eventually the factorial will start to include numbers that are higher than 100. Once you get to the 100th factorial, you're multiplying all numbers from 100 and down. But anything past that is going to start to include higher and higher numbers. And eventually that factorial, because it's including larger and larger values, will beat any one number taken to a consistent power. On the flip side, if you take some number taken to the power of itself, that's always going to be n factorial. This is like 2 factorial compared to 2 to the second power. Well, 2 to the second power is 2 times 2. If you do 3 factorial compared to 3 to the third power, well, 3 factorial is 1 times 2 times 3, where 3 to the third is 3 times 3 times 3. So whereas factorial has the weakness of always multiplying numbers below that highest value, n to the n will always take that highest value and multiply by itself the same amount of times. It's important to recognize this strength because then you can start to go into some examples and see, okay, well, I know that one's going to be bigger, so I can probably have an idea of what this limit's going to look like. But it's good to kind of understand these. Overall, I have a few examples here for ratio test, and then we're also going to have a couple for the root test as well. The ratio test and root test, if you notice, I don't have much space here saved, and there's a reason for that. These don't take too much time, which is again why a lot of people really like the ratio and root tests. Okay, now what we again need to keep in mind are the values for the limits. If L is less than 1, we have absolute convergence. If L is greater than 1, we have divergence. If L is equal to 1, it's inconclusive. If it's inconclusive, that means another test needs to be done, which can very easily happen. All right. So for example 3, we have for determining convergence or divergence, we have k divided by e to the k. Notice the denominator here, e to the k, this is an r to the n situation. This is some solid value e taken to an increasing power dependent on the series value. This is going to be our key of saying, okay, maybe the ratio test would be interesting. So let's try that. We want to find the limits as n approaches infinity of the absolute value of, in this case, this is k, so a to the k plus 1 over a sub k. The absolute value is irrelevant here because there is no negative 1, so we can kind of drop that as k approaches infinity. And if we have, we could drop the absolute value. If we have a sub k plus 1, we just put in k plus 1 to each of these. So we have k plus 1 divided by e to the k plus 1. All that is divided by the original value, k divided by e to the k power. If we rearrange this a bit, combine the algebraic and combine the exponential, we have overall k plus 1 divided by k, and we also have e to the k divided by e to the k plus 1. Now, when evaluating what happens as this limit goes to infinity, we should be able to evaluate this now. However, you can move a little bit further if you want to go with e. For example, you could say limit as k approaches infinity of k plus 1 divided by k, and that's e to the k over e to the k plus 1. That'll subtract the exponents, and you'll have e to the k to the negative 1 power. So you have 1 over e. Now, we could have done that earlier, but now we can also evaluate this limit because k plus 1 divided by k, as the leading term test says, because both the top and the bottom have the same degree of 1 as the highest, we can just take the coefficients of up front, 1 over 1. So this goes to 1 over 1, or 1. That means overall, this goes to 1 times 1 over e, or just 1 over e. That's our value of the limit, and since the value of the limit, 1 over e, is less than 1, this converges absolutely by the ratio test. And that's it. That's the ratio test. This is why these go pretty quick. You just do a limit, which most of the times you don't even need to do L'Hopital's to solve them. A lot of the times, once you have the ratio set up and you get to this place, you should be able to evaluate the limit directly. But let's do a couple more examples so you start to see this. Alright, so far we've shown that r to the n is more powerful than just a variable, so just k. But let's see what happens when we compare a couple of these. So here we have a situation where we have r to the n, and here we have a situation of n factorial. This again is pointing out that, hey, maybe the ratio test would be a good idea. Specifically n factorial. N factorial you should really only do with the ratio test. We've done an example of that before, and they're really hard to work with. Okay. So again, the absolute value is irrelevant here because all these terms will always be positive for n being 1 to infinity, so that's fine. And one way of doing this, because if you noticed last time, we're always just going to really be multiplying by the reciprocal of the bottom, you can do this a little bit faster by just taking a sub n plus 1, which in this case would be 8 to the n plus 1, divided by n plus 1 factorial, and then multiply by the reciprocal of the bottom of a sub n. The reciprocal of the bottom would be n factorial divided by a to 8 to the n power. This is nice because it's a little bit easier to see what combines well here. 8 to the n plus 1 divided by 8 to the n will just leave you with a value of 8. Times n factorial over n plus 1 factorial. Now, for those that need a refresher of factorial, remember that factorial just multiplies that number and all the integers less than that. So this is n times n minus 1 times n minus 2, etc. Whereas this one is n plus 1 times n minus 1 times n minus 2, etc. Which means that the n's will cancel, n minus 1 will cancel, n minus 2 will cancel. All those will cancel except n plus 1. So this becomes the limit as n approaches infinity of 8 times 1 over n plus 1. Which this limit of 8 times 1 over n plus 1, goes to 8 over infinity, which is 0. With that value of the limit, we say that since 0 is less than 1, this series is absolutely convergent. Okay. Now, note at the top of the page, I talked about the strength of these. I talked about how r sub n is not as strong as n factorial. This is saying that n factorial will get bigger faster. That's why when we looked at this, we saw 8 to the n over n factorial. We should be thinking that, okay, eventually that denominator is always going to be infinitely larger than 8 to the n. So this should start to go to 0. This should hopefully be convergent. We can start to get that idea. If you had this flipped, if you instead had n factorial over 8 to the n, we would think that that would diverge because n factorial is going to be stronger than 8 to the n. And we evaluate these in terms of limits, whichever one goes to infinity faster. In this case, 8 to the n does not go to infinity as fast as n factorial does. So that's why I said it's good to recognize the strengths, because then you can start to go into a problem and get an idea of what's going to happen there. Okay. Another one. Whether this is convergent or divergent. We have 2 to the n over a natural log of m. Now, we had the first example of k over e to the k, and we showed that e to the k won over a constant term. We know that natural log is very slow, and 2 to the n should be a lot faster. So we think this probably diverges, because 2 to the n will go to infinity a lot faster than natural log of n. And here we actually are evaluating the limit of it. Well, the limit of the ratio anyway. So we're thinking that it's probably going to diverge, but let's check that. Again, seeing 2 to the n, which is r to the n, that's a hint that maybe the ratio test would be a good idea. So we do the limit as n approaches infinity of a sub n plus 1 over a sub n. Again, the absolute value doesn't matter here, and really this n actually should go from 2 to infinity because the bottom is natural log of n. But this really won't matter because all these terms will always be positive, so it's fine. And we can instead multiply by reciprocals. So take n plus 1, put in for n, so we have 2 to the n plus 1 divided by natural log of n plus 1. And multiplied by the reciprocal of what we have originally, natural log of n divided by 2 to the n. This, if we rearrange, this will give us 2 to the n plus 1 divided by 2 to the n, which just gives us a positive 2, times natural log of n divided by natural log of n plus 1. Now you can probably expect what this goes to, but if you're not sure, you can always do L'Hopital's. So we could do L'Hopital's on this, because it is technically indeterminate. Natural log of n will become 1 over n. Natural log of n plus 1 will become 1 over n plus 1. So this is the limits as n approaches infinity of 2 times n plus 1 over n. And now we know what that definitely goes to by the leading terms test. They both have the same leading power of 1. So we know that this should go to 1 itself. That means that this becomes 2 times 1, So this overall limit evaluates to 2. Now be careful here. The limit going to 2 doesn't mean it's convergent. By our conditions at the top, I wrote them on the side here, but if we even look at the original definition, if L is less than 1, it's convergent. But if L is greater than 1, the series is divergent. And that's what we have in this case. Since 2 is greater than 1, this series diverges by the ratio test. Which I also didn't include the past one, ratio test. There we go. And that agreed with what we thought might happen, that it would diverge. Now I will say, you can use that trick of looking at r to the n factorial, and n to the n, of thinking about which is going to be faster when, to get an idea of whether it's convergent or divergent, but don't just look at those and say and identify, oh, that's probably going to be divergent, and move on. You always need to show it, so still show all the work for the ratio test, but that can give you an idea of where your work is probably going. Let's do one more. Sum of n to the n over n factorial. I think we actually did this one earlier, or n factorial over n to the n, a few sections ago, and it was hard to evaluate. We had to do some math finagling to try to understand how we can work with n to the n or n factorial. But here with the ratio test, it's a lot simpler. Now, again, we see n to the n and we see n factorial. These are big hints of the ratio test, but we should also have an idea of what's going to happen here. As we showed before, n factorial is going to be less than n to the n in terms of strength. So we expect, because the top is n to the n, and that's going to be infinitely bigger, we expect divergence here. Because it looks like the top is going to go to infinity faster than the bottom does. But let's show that. Alright. Limit a sub n plus 1 over a sub n. Again, the absolute value doesn't matter here. This again is helpful for if there was a negative 1 to the n minus 1 up front there. The absolute value would kill that off, so it becomes irrelevant. This is why it's also really good for alternating series. But if we multiply by the ratio of these n plus 1 terms, so we have n plus 1 to the n plus 1 divided by n plus 1 factorial times the reciprocal of what we have originally, n factorial over n to the n. Alright. Now let's see what we can do here. If we rearrange some stuff, I can rearrange the factorials, and we can also rearrange the n's. First, the factorials. I have n factorial over n plus 1 factorial, which we should understand how to work with because we did that before. But we also have n plus 1 to the n plus 1 over n to the n. Now here, we see n plus 1 and n plus 1. And on the bottom, we have an exponent of n. So we can actually take out one of those n plus 1s, like so. That way, these two both have the same power. That will allow us to reevaluate this limit. N factorial over n plus 1 factorial. We showed before that there's only going to be one term left over from n plus 1. So we're going to have 1 over n plus 1 times, in this case, n plus 1 divided by n to the n power times n plus 1. This n plus 1 and that n plus 1 will cancel out. And so all we have is the limits as n approaches infinity of n plus 1 divided by n to the n power. Or if you rearrange stuff in the middle, you divide that n into both terms on top. You have n divided by n as 1, plus 1 divided by n is 1 over n to the n power. This 1 plus 1 over n to the n, That limit is very particular. That's an incredibly famous limit. A 1 plus 1 over n to the n power. This limit as n approaches infinity is defined as e. This is the definition of e, which I know I've gone through in class before, so hopefully that should be familiar with you. But if not, that is the definition of e, and that's something that you should hopefully want to recognize moving forward. You can also try plugging in values of n, even up to 100, and start seeing what's happening. You should get closer and closer to 2.71828. Now again, like last time, just because it's going to e, it's going to one number, does not mean the overall series is convergent. Actually, e is greater than 1. So by the ratio test, this series diverges, which is what we expected. So that's how you would deal with n to the n over n factorial. Okay. Now those are all examples of using the ratio test. Again, if you see any of those kinds of things, the ratio test is great. If you see everything taken to an n power, either together or not, the ratio or the root test would possibly be better. For example 7, we have negative 2 to the n power divided by n to the n power. You could do the ratio test here, but the root test is actually going to be a little bit cleaner. And with the root test, what we do is we take the limits as n approaches infinity of the nth root of a to the n. Specifically of the absolute value of a to the n. That absolute value there is going to kill off that negative 2, or that negative anyway, it's not going to matter. So what we're really dealing with is the limits as n approaches infinity of the nth root of 2 to the n divided by n to the n. Since they're all taken to the n power, when we take the nth root, that will actually take away the power. So what we have here is the limit of 2 to the n taking out the power, you just have 2, divided by n to the n, taking out the power, we just have n. And this limit goes to 2 over infinity, that goes to 0. Now remember, the ratio and root test have the same conclusions. 0 is less than 1. So by the root test, this series converges. Absolutely. If you got an inconclusive result here, you can always check to see if it converges conditionally using other tests. Lastly, number 8, the sum of negative quantity 2 to 2n over n plus 1 to the 5n. We don't have a full power of n, but we have some amounts of it. That's still a good hint of the root test, so let's try that. Limits as n approaches infinity of the nth root of the absolute value of a sub n. Notice we don't even need to compare multiple versions of this, just the original. That's also why the root test is a little bit nicer sometimes. So we want the nth root of, in this case, the negative will be taken out from the absolute value. So we have 2n over n plus 1 to the 5n power. The n and that n will cancel out because that'll be 5n times 1 over n. And you'll have limits as n approaches infinity of 2n over n plus 1 to the 5th power. We can move that limit inside of the function. So we have the limit as n approaches infinity of 2n over n plus 1 all to the 5th power. And this limit we can evaluate by leading terms test. The leading terms have the same power. 2n over n means that this limit is going to approach 2, or 2 over 1. And 2 to the 5th power is 32. In this case, since 32 is greater than 1, we have, so by the root test, this series diverges. And that's it. So these tests aren't really too bad. They just kind of evaluate limits, and I don't think we did L'Hopital's on any of these. Did we do L'Hopital's once? Technically, we did it back here with natural log of n over natural log of n plus 1, but that's not exactly necessary. You can still evaluate that as going to 1, because you can actually move the limit inside those natural logs if necessary. So kind of unnecessary to do L'Hopital's, but you can. Most of the time, you don't even need to do it. These series tests, root and ratio, are fan favorites because they're so quick and easy, and they evaluate these things that otherwise you would have no idea of. You can even look back at a lot of the series that you've done in the past, and you could probably evaluate those with ratio tests, or at least some of them. In terms of hierarchy, these go a little bit higher than things like the integral test, and usually comparison tests is usually recommended you try this before the comparison tests or integral tests, unless it is a basic P series or geometric series. Those you should be able to do directly, but after that, maybe see if this can work, or the alternating series test possibly. All right, if you have any questions, feel free to put those in the comments below, or you can ask your instructor directly. With that said, I hope you have a nice day.